Audio. And now that we're recording. All right, everyone. Welcome to our webinar today. For those of you online, we do have a live audience here at the Freedom Center. So I'm Ken Delaney. I'm the industry liaison for Freedom. We are the Power Electronics and Power Research Center at North Carolina State University. We have a dozen faculty, over 100 graduate students, and about $6 million a year in research that's funded through federal agencies, corporate sponsors, and state level projects. We have a lot of labs, including our high bay, where we conduct high power testing up to 15 kV. And I'm going to advance to the next slide. There we go. Just a quick introduction. FREEDM stands for Future Renewable Electric Energy Delivery and Management. We started in 2008 as a National Science Foundation Engineering Research Center, and today we categorize our research into 4 pillars: wide bandgap power electronics, which must be my next slide. There we go. Wide bandgap power electronics, electric transportation, modern power systems, and renewable energy. Projects can bridge, of course, multiple pillars, like when we develop silicon carbide solutions for renewable energy applications. Our industry members engage with the center in multiple ways, including leveraging research funding as project partners, early access to intellectual property, discounts on testing services in our labs, and of course, interactions with our students. Today's speaker is Shweta Meena, who received her bachelor's degree in electrical engineering with a focus on power and automation from the Indian Institute of Technology in Delhi, India, in 2020. She is currently pursuing her PhD degree here at Freedom at NC State. Her research interests include microgrids, optimization, machine learning, and controls. All attendees are muted, so please enter your questions through the chat, and then I'll ask those as we go along. Shweta, it's all yours.
Hi, everyone. Good afternoon. Thank you for joining for this presentation. So the title of my presentation is Plant Control Co-Design Approach for AC Microgrids.
I'm going to adjust your camera so we can see you.
So this is the outline of my presentation. So first I'll talk about the project this research is part of, why this research is important, and then I'll talk about our proposed co-design framework for microgrids, and then a case study on Benchu distribution feeder, and what is our path forward with this co-design research. So this research on co-design is part of the project Microgrid Control Coordination Co-Design funded by the ARPA. The goal of this project is to create a microgrid design tool that outputs optimal microgrid designs, which are cost-effective, stable in different scenarios, and have a predictable dynamic performance, given a set of design requirements. This microgrid design tool suite has 2 main components, the design time tool and the operation time tool. In the design time tool, we generate optimal microgrid configurations using the co-design framework, which I will discuss in this presentation. We design both the plant, which is the DR, type, size, and placement, and also the control gains for the microgrid. The output microgrid designs are validated using high fidelity simulations, using hardware in loop simulations, and the operation time tool is executed on a modular control platform, RIAPS. The main motivation behind this project is to increase the deployment of microgrids and to facilitate higher penetration of renewable energy resources in our grid. This project is a joint collaboration between NC State University and Vanderbilt University. NC State is leading the research on co-design, working on the design time tool, and Vanderbilt University is helping us in translating this research into a practical design tool and working on the operation time tool. So I'll start with first introducing what is a microgrid. So a microgrid is a group of distributed energy resources and loads within a clearly defined electrical boundary. It can operate independently or in conjunction with the main grid. The main advantage of microgrids is that they increase the resiliency of distribution systems during extreme weather events like hurricane and floods. In addition, they also facilitate integration of renewable energy resources at scale. Similar to any other complex engineering system, a microgrid has 2 design domains. the physical infrastructure, which is the DR type, size, and placement of energy resources, the microgrid topology, and the control architecture, which includes the controller design for individual DERs and also the system level control. Despite this potential, microgrids haven't been widely implemented. The reason being, current industry practice to designing microgrids is inefficient. Firstly, the plant is only designed based on economic factors, and only then are the control algorithms integrated to ensure system stability and meet the dynamic performance requirements. The disadvantage of this approach is it is possible that with the chosen mix of DRs, just based on economics, the system cannot meet the stability and the dynamic performance matrix. And as a result, design iterations have to be made, which results in project delays and increased cost. And even if the dynamic performance and stability requirements were met, it is possible that with another mix of DR, dynamic performance could have been better. A simple example is the minimum cost design would be like a microgrid with two synchronous generators, as they are cheaper as compared to battery energy storage systems. But they experience rotor angle stability during faults and require fast responding batteries, which can provide voltage and frequency control. And hence, for optimal microgrid design, it is important to optimize both the plant and control simultaneously. In this presentation, when I talk about controls, I am referring to the primary control layer in the hierarchical control structure of the inverter-based resources, which manages the real and reactive power sharing between the DERs. In this research, we are not modeling the inner power electronic voltage and current loops, as their response is significantly faster in comparison to the primary control layer. State-of-the-art addresses microgrid design in two ways. Firstly, enhancing microgrid dynamic performance by fixing the control gains and only modifying the plant, that is, changing the DR type, size, and placement. The second category of microgrid design approach is where plant is fixed and only control gains are modified to improve the dynamic performance of the system. I'll start with first discussing the plant-based approaches. In this also, we have two subcategories. The first category focuses on steady state objectives like choosing the DER mix and their placement to minimize voltage drop in the system, power loss in the system, and load curtailment goals. And in other subcategory, we have a set of pre-existing DERs, and the new DER is installed such that the dynamic power response for the existing DERs has a similar transient overshoot, or with the addition of the new DER, the response in fault is improved by minimizing the deviation in bus voltage and an angle. The limitation of these approaches is they only vary the physical infrastructure, the type, size, and placement, and the control gains are fixed. As a result, the dynamic performance of the microgrid is suboptimal. Now talking about the second category, where the physical architecture of the microgrid is kept fixed and only the control gains are tuned to improve dynamic performance. We again have two subcategories. The first subcategory is the small signal based approaches, which minimize the H infinity H2 norm of the system with the goal of minimizing deviation in frequency, rock-off, and power. The disadvantage of the small signal based approaches is they cannot ensure system stability for large signal disturbances like islanding or faults. And the second subcategory is the large signal based approaches, in which particle swarm optimization and like simplex based approaches have been used to minimize like power tracking error, voltage tracking error. But in the literature, these studies have only done for very simple microgrid systems with like one inverter connected to the grid. And as a result, this non-linear stability approaches have not been generalized for large-scale microgrids. To sum up, in the literature, the coupling between the plant, the DR type, size, and placement, and the control gains and the dynamic performance of the microgrid is not taken into consideration during the design process. And to address this problem, we have proposed an integrated plant control design framework that simultaneously finds the optimal type, size, and placement and control gains with the objective of optimizing cost, stability in grid connected and islanded mode, large signal stability, improved dynamic performance, and adherence to grid codes. Now I want to highlight the key features of this framework. So this framework that we have proposed differs from the state of the art in three different areas. First is the plant controller coupling. In our framework, we explore the entire feasible plant control design space to arrive at the optimal microgrid plant and controller design. Unlike the state of the art, where one is fixed and only the other domain is optimized. In our framework, we have evaluation using EMT simulation, which can ensure large signal stability of the system during islanding and fault events. While in the state of the art, only small signal evaluations have been considered. And in our framework, we tune the control gains for both grid connected and islanded mode in adherence to grid codes and this large signal stability evaluations, which is not done by the small signal based approaches. The motivation for this co-design approach for microgrids came from the mechanical systems, where co-design has been extensively applied and promising results have been obtained for the design of automotive suspension, spacecraft, and design of wind farms. Now, this is the vision of our co-design framework. On the left is the flowchart of our co-design approach. So to design a microgrid, we typically need inputs like the topology of the microgrid. What is the number of buses in this microgrid? How are these buses? What is the connectivity of these buses? The transformer locations, the breaker locations, and the system load location. Next, we need what type of DRs we want to install in this microgrid and what is their corresponding cost. What is the weather and the load data for this particular area that we are designing the microgrid. And if there are some site-specific constraints like the total number of DRs that can be installed or some of the sites where DR cannot be installed. All these inputs are passed to our microgrid plant optimization framework, which is essentially a standard microgrid planning algorithm, but it not only finds the minimum cost design, but it finds all the feasible type, size, and placement of energy resources that satisfy the power flow constraints, DR's specific constraints like the battery SOC constraints, and any user specific constraints. So this can be visualized using this picture here. So this microgrid plant optimization starts with a very large design space. For example, a 10,000 design space if we have 10 DRs and we have a 17 bus system. And then we have, and it is very computationally efficient as such a large plant design space can be generated in less than a minute. And then we have fast analytical checks just by adding some algebraic evaluations. We prune this design space to reduce the number of plant designs that we want to evaluate using EMT simulations. And we have added constraints for like motor start and islanding in our framework. And now this feasible set of designs after the pruning, these are passed to the control optimization framework for stability analysis. And now from the entire microgrid planning period, we choose a critical operating point where we analyze the stability of the system. So one example can be the point where microgrid is importing maximum power from the grid and if it is islanded. So that would be one critical point to evaluate system performance. And in this microgrid control optimization, we use a non-linear model of the system to evaluate the large signal performance during islanding events, and we tune the control gains in grid connected and islanded mode to maximize a performance metric, which I will discuss later in this presentation. So we can see that using this co-design framework, we have a set of plant designs and a corresponding control gains. And these plant designs have variation in cost and some have only variation in placement. So this finally gives us a trade-off between cost and dynamic performance. And this is our vision of going ahead. So currently we have a large set of plant designs that we evaluate using EMT simulations. But going ahead, we want to use an iterative co-design approach where we will use the neural network to learn the information from the data that we have using EMT simulations. and it will capture the relation between the type, size, and placement of energy resources in a microgrid and the dynamic performance. And then we will only evaluate the top X designs instead of evaluating all the feasible designs. So now I will go into the details of each of this block to give some more context. The microgrid plant optimization is a mixed integer linear programming formulation. It is coded in Python and we use the Gurobi solver. And instead of just minimizing the cost, it is a metric that we evaluate and we find all the feasible set of designs. So this is one example of how this algorithm works. So for example, if we have 3 buses in the system and we have an option to install either batteries or diesel generators, we will have total 8 combinations. And out of this, the design, which has all the diesel generators, is the minimum cost design. And this is a visualization of how the branch and bound algorithm in the mixed integer linear programming works to find the feasible solutions. And we can see that the standard microgrid planning approaches only focus on the minimum cost, but we focus both on this blue and the green solutions. Next is the control optimization block. So here the goal is to minimize a cost function, which is related to the dynamic performance metric and adhere to grid standards like IEEE 1547 standard. And we evaluate this optimal control gains using particle swarm optimization with EMT simulations in loop. And these are the metrics that currently our tool is capable of evaluating. So that since it is based on a non-linear model, it can evaluate both large signal and small signal performance metrics like eigenvalue analysis, integral absolute error in power tracking, critical clearing time during a fault, and the integral absolute error in voltage and frequency dynamics during a transient. And other metrics can also be added going ahead. This is how the DRs are modeled in a framework. So for each DR, we develop a nonlinear differential algebraic equation-based model in MATLAB. The grid forming inverter is modeled as a controlled voltage source with the outer power droop loop, and the tunable parameters are the droop and the low pass filter gain. For the grid following inverter, it is modeled as a controlled current source with outer power loop, which is a PI control loop, and the tunable parameters are the gains of this PI controller. And this is how the overall non-linear model of the system looks like. So we have equations related to the DERs, grid forming, grid following inverters, and the network dynamics, which includes the line dynamics and the load dynamics. So here, currently we only have inverter-based resources in our model because we were focusing on studies with 100% IBR penetration. But going ahead, we will include other DR models as well. And this is the final output of the co-design framework. We have a set of feasible plant designs for a given microgrid design requirements that vary in type, size, placement, cost. And for each of them, we have the optimal control gains in both grid connected and islanded mode. We have also translated this research into an actual design tool. So we have this automated framework and we can run it for any microgrid topology. So the only inputs that it needs from the user is a microgrid topology, a database of the DRs, what is the weather and the load data, what are the different scenarios that we want to simulate, islanding faults, and what are the system performance metrics that we want to evaluate. And then this automated framework produces the results in a human readable format, which is like a CSV file, which captures all the information regarding different plant designs, what is the location of DRs in each of the design, and what is the corresponding optimal control gains. And we have developed this with the help of Vanderbilt University. And now, talking about the computational complexity of the framework. Plant optimization, it has a computation time of seconds to minutes. As we have seen in the previous slides, it can generate more than 10,000 plant designs in fraction of minutes. And for the control optimization, for per design, like for one a microgrid topology with specific placement of DRs. So for example, if we have 3 DRs, it takes 20 minutes, and as the DRs increase, the number of tunable parameters increase and the computation time increases. And in order to evaluate these large design spaces of like thousands of designs, we use the parallel computing services at NC State. And this allows us to evaluate roughly 200 designs in parallel. This is the overall summary of our co-design framework. So it can evaluate steady state metrics like the system cost, which consists of investment and operation cost. It can evaluate steady state constraints like power flow and DR capacity constraints, and dynamic constraints like rock-off and frequency constraints. Currently, we are measuring the resiliency of a microgrid if it can handle an unplanned islanding event, and the voltage and frequency stability are measured using adherence to IEEE 1547 standard. And our performance matrix is the integral absolute error, which I will discuss in detail in the case study. We are using the Benchy distribution feeder as our test system. It is a standard test system for microgrid studies. So we are operating these two feeders together as one microgrid, and bus 101 is the point where the system is connected to the main grid. Our entire analysis is done in per unit, even though the system has different voltage levels. So we translate the system into a one line diagram, and then we do our analysis. So this is how our integral absolute error matrix is evaluated. In grid connected mode, it measures the error in power tracking. So for a step change in DER, how fast will the DR respond to this change is evaluated. And in islanded mode, a load step change is given for all the loads in the system, and how fast can these DERs damp this disturbance. So for an example of two battery case with this Benchy distribution feeder, this is how we can visualize the results from planned design exploration. So the entire matrix is the possible placements, the combinatorial possible placements, and the red ones, which are infeasible, they are infeasible either due to power flow constraints. And in this case, I have given example where we also evaluate the unplanned islanding constraint just by using algebraic evaluations. So our planned design space can eliminate designs that will have steady state voltage violation after islanding, as I have shown in this figure. So this prunes a large design space to a subset of designs. And now for one design from this feasible blue region, where, for example, we have batteries at buses 2 and 3, this is how the control design space exploration looks like. So we are trying to visualize this using this matrix of possible control gains for the two grid forming inverters. And our evaluation can separate this region into stable areas, unstable areas, and identify which regions will have violations with IEEE 1547 standard, like the rock-off and the frequency violation. And we can see that if any random controller gain, which is like the standard 5% droop in LPF is selected, it can still have rock-off violation. So it is important to evaluate the stability of the microgrid while designing the microgrid. And from this stable region, optimal controller gains are chosen, which minimize the IAE matrix that I discussed earlier. And this is how the overall output of the score design frameworks looks like for a two battery case, where we have all the possible buses. Some of them are infeasible just because of steady state evaluations. And for each of the feasible buses, we have the optimal gains in grid connected mode, islanded mode, and also the dynamic performance matrix to compare different placements. Now I will share some interesting results that we have got using this co-design framework. So for the example case of these two battery systems in grid connected and islanded mode, even if the controller gains are tuned to minimize the IAE matrix for two different placements, still the placement has an effect on the dynamic performance of the DERs. And we can see that even with optimal controller, the design with an optimal placement tracks the response faster in comparison to a suboptimal placement. And this becomes more prominent when the number of DRs increase in the system. And this shows that placement also has an impact on dynamic performance. So it is important to explore the different DR configurations and just not one placement and the minimum cost design. And here we have explored the co-design framework with like a wider range of DR portfolio where we have batteries and PVs. And here we have explored the different placements for each DR configuration. So our tool gives the trade-off between cost and dynamic performance and the different placements for each DR type. So if we used a standard microgrid design tool like DR CAM, it would only give us like one solution for this microgrid design problem, which is minimum cost. And the placement would be selected based on like minimizing system loss. But that placement might not be the best one in terms of dynamic performance. And as a result, this tool gives the user complete visibility to how to choose the best placement and the type of DRs when designing the microgrid. So we have also tested this framework with like a large system like 10 batteries, so which demonstrates the scalability of this framework, and then that it is applicable for large scale microgrids. And in this case, we had 3000 designs for this particular configuration. And going ahead, we want to evaluate larger design spaces with like addition of other types of DRs like synchronous generator, flywheels, and supercapacitor. And also evaluate other contingencies like faults, black start, induction motor start, and add more matrix in the toolchain in addition to the power tracking error matrix like critical clearing time during a fault. And I would like to thank my colleagues from the Micro C3 project, Ayman and Scott, who have also contributed to this work. And these are the references that I have used in this presentation. And yeah, thank you for listening to me patiently. And yeah, let me know if you have any questions.
Yeah, great presentation. So in the beginning, you mentioned that if we just have a microgrid with only synchronous generator, then it experiences a rotor angle instability. So is it because of a very high dynamic load profile in the distribution network, or is it because of the low accuracy of the forecast, load forecast at the distribution level of load?
So the question is for the people on Zoom that why does the system experience instability when there are only two synchronous generators in the system? Is it because of the low accuracy of the load forecast? So in my understanding, the issue with the rotor angle instability is due to the slow response of the synchronous generators during a fault and the interactions between them. So the load forecast is not the major factor here.
So, so you spoken about AC microgrid, but can this tool be extended for DC microgrids also? And if you were to do it, how would you change it?
Okay, so the question is that this approach has been discussed for AC microgrids, and can it be applied to DC microgrids, and what things would have to be changed? So it cannot be directly applied to DC microgrids because the planning formulation, the power flow is for like AC systems and also the AMT evaluation. But the approach can be applied, but the pieces will change. Like the microgrid planning problem, it would have a different formulation for the DC microgrid. And yeah, and the models of the DERs and the control evaluation will also like change.
Hey, this is Shahab Afshar from North Carolina Electric. So thank you for the presentation. My question is, what's the advantage of this tool over like other commercial tools like Homer or Zendy or some other available tool in the market? And how do you imagine this will be used? Because I see the sizing and placement part. I don't see the feasibility, or maybe I don't I don't notice if you explained that part or not, but have you done any feasibility study to where we actually place the microgrid, or have you done anything like that in your model? Sorry, there were multiple questions.
Yeah, so starting with so the difference between the commercial tools available like Homer, DR, Cam, Zendy, and our tool is, so they only design the microgrid from the economics perspective. So for example, they will only have a minimum cost design and the placement based on a steady state metric like power loss or the voltage in the system. But here we also have the dynamic performance evaluation using like EMT simulation. So for each of the, for example, for a fixed DR configuration, for each possible placement, we are doing this EMT simulations. And in grid connected mode, we are measuring the power tracking error in the DR. In islanded mode, we have the load step changes. And then we are also measuring adherence to like 1547 standard. So with our tool, like the final microgrid design will not only have like the best cost, but also that it would be stable during an islanding event, for example, that we have shown here. And the control gains will be such that the tracking performance is the optimum. Does that answer your question?
Yes, and about the feasibility aspect, have you done anything like geotech study or something like that can be included in your model for the right placement of microgrid or the best location, finding the feasible locations?
So
Just
in this,
asking to get familiar with what you have done.
So in this, we have the microgrid topology fixed and we decide the location of the DERs. But this framework is not to decide the location of microgrid in a geographical area. Here, the focus is to design the microgrid given the geographical area is fixed.
Thank you.
Just trying to understand. So this is like a centralized control microgrid, right?
So each DER has their own control, which is like the droop control for grid forming and the PI control for the grid following.
And all these, do they have like a centralized control, like an aggregated control for all the DERs, or they are all decentralized?
So it is decentralized. We are not using any system level controller here.
So in the modeling phase, it is assumed that we have the internal control data, the data of the internal control loops, right? But if we have like a manufacturer who is not willing to share the internal data of their system, so how does that impact the co-design?
So the question is, if a manufacturer is not willing to share the internal data related to the controller gains of their DRs, how will this approach change? So if we cannot modify the control gains of the DRs, then we will have to come with a different approach where our controller is is used in parallel to the existing controllers, and that would be a separate approach.
I like that question because it relates to something I was curious about. How are we receiving data from manufacturers, or have we asked them for something?
No, they don't say that.
No. So, yeah, okay, so from the audience, they said we don't share that information.
Like we are not asking them, like we need access like here in the study for like tuning the droop and the low pass filter gains.
Yeah, so what would it take for a manufacturer to share some of that information with us?
So we asked that, for one of our project tasks. So they just share the schematics, nothing else. So what we know about everything, let's say we are talking about a DC microgrid with 3 ports, let's say that we have 3 converters. So they will share with you that there is a GUI or graphical user interface that you have like what you can do with each of the ports. Like you can do the current control, power, you can have a group also. So you can just get that information, nothing else. So they don't even share the control strategy, that's what they have used and all this. So they don't actually share it. So we tried several times, but what they give is just a skeleton of it. Like,
I think it also depends on the manufacturer, for example, at Emirates, they have Dynapower and EPC inverters. Over there, they do have access to the dual fuel for all of them, and they also have access to the fuel perspective. So I think if there is some sort of agreement between the manufacturer, these things can be adjusted. Have access to
Okay, so at the national labs, they may have access to those internal loops, yeah. Okay.
but some of the microchip that we have in our section, the CEP,
Mhm.
so they don't share any.
Right,
Nothing.
so that's part of the struggle is
So it's- yeah,
to be able to get the information to populate this tool so that it truly can determine, because you can not only, does your tool allow you to evaluate different inverters from different manufacturers?
Yeah, like we can, since we have this AMT evaluation integrated, we
Yeah.
can evaluate like if we have two different designs with each with different types of inverters, we can compare their performance.
So like I would say, if you had a Dynapower and an EPC inverter, you could use one, use both, have multiples to be able to, and have that as a parameter on which you optimize.
Yes, we can do that.
Okay. Yeah. Good question.
I think with time, they will become more flexible. The manufacturer sharing like it.
Might be an IP issue also.
Yeah. Currently, they have. With
Mhm.
time, they should be a bit more flexible.
Yeah. Okay. Can you ask the attendees online if they have any questions?
Does anyone online have any questions? Please feel free to put them in the chat or unmute yourself and ask.
So while we're waiting on them, I have another question. Aside from getting data from manufacturers, what was the hardest part of this project?
So the hardest part was building this framework. So coming up with this idea of how to combine this like the type size and placement and the control evaluation problem. Because in the standard co-design approaches, it is simpler for them because they have an objective function which has both the plant cost and the control cost. But here it is difficult to derive any analytical relation, like for this large non-linear model of microgrids and like the this physical parameters, the type size and placement and the dynamic performance. So we had to use like this EMT simulations in loop. So to come up with the overall idea of the framework, how to like do this code design, integrate the two pieces and make it generalized for like different microgrids.
And you mentioned multiple mechanical scenarios or mechanical problems where co-design has worked. Are there other examples of electrical related problems for co-design?
So it has not been applied for plant control co-design.
Okay.
Some people have done with like the Siemens is working with protection co-design.
Ah, okay. Mhm. Okay.
Follow up on your inverters, so there are many types of inverters that we can connect to the grid, right? So you can, I mean, you can have, within BSIs, you have like 5-6 different popular types, and then you could even put current source inverters there. And there is a strong argument as to why you should be even thinking about it. How does your model distinguish between them? Because their grid interaction is not the same, the way different inverters interact with the grid.
Yeah, so the framework differentiates between like the different type of inverters, for example, grid forming and grid
No,
falling.
no. Saying like the topology itself, you can have a 2-level converter, or you can have a multi-level converter, or you can have a series connected, CHP thing that we are doing downstairs, the XFPT is doing downstairs. They all interact very differently with the AC port, like with the interconnected points. So is there any flexibility to include those things?
So you're saying like different inverters like with different dynamic responses?
Yeah, because the topology also drives how quickly you can move power.
But when you're saying the topology is different, but is the response of the outer power loop different, or is that response the same?
Inverter, so let's say you give a command, not every inverter responds at the same amount of time.
Yeah, so we can like have different inverter types integrated in this framework. There is no limitation. We just need to have an equation-based model of that particular topology integrated, and then we can compare the performance of different inverters. And these are just examples that we have currently used, but like right now we are working to integrate synchronous generators. So there is no limitation of which type of DERs that we can integrate.
Shweta, we do have a question in the chat. So if we have mixed DC and AC buses in the microgrid, as in the case where an SST is used, how can you do optimization of both?
So if we had a mixed AC and DC, then the approach will have to change. The power flow will have to change to account for both the AC and DC. And the controller evaluation. Like the overall approach would still remain the same, like generating the designs and evaluating the control performance. But like the internal algorithms will change because currently it is only designed for like AC microgrids.
So that's next semester, you'll add DC.
That would be a separate project
Okay.
because DC has completely different formulations and the like the control models.
And so the follow-up to that is how can you include resilience in your optimization?
So currently we are evaluating like 1547 standard during the islanding event. So this is our, sorry, my screen has. So currently we are evaluating 1547 standard during an islanding event. So currently like our resiliency matrix is that if can the system survive an islanding event. And for like faults, we have different matrix like critical clearing time during a fault. So we measure the system resiliency during using this performance matrix. I want to go to that slide, but I think my screen is frozen.
But that's the one you showed that has the red and blue.
The one which has all the different performance matrix, like, so we measure the resiliency using this different performance matrix. Yeah, so these are the like different matrix that we can evaluate. And for example, the critical clearing time, it is a measure of resiliency. So for the system can survive a fault for a longer period of time, the more resilient is the system.
Okay. Good point. Any other questions from the room? Oh,
Sure.
one.
All right, so in your case study, what was the, let's say, power rating of the various DERs that you took in place? Okay, we have like, let's say, a megawatt class converter and then a kilowatt class converter in the same, principally a similar network, or should they all be of a similar rating for your tool to function correctly?
There is no restriction that they all have to be in the similar size range. So these are what we have used, which were like different sizes in the megawatt range. But even if it was kilowatt, there is no like restrictions in the tool for the size.
So you can mix high power and relatively low power DDR.
Yes.
Okay. We do not have any more questions online, but thank you very much. That was really good. So I'm going to come up and stop the recording. Thanks everyone online for joining us. And if PowerPoint is going to cooperate, we will just, how did you stop the recording? Okay. Thanks everyone for joining us, and look for a note about our next webinar. Also, this recording will be online and we'll send out a note about that pretty soon. Thank you so much.